Okay, so now let's look at some examples for the chain rule. First example, find the derivative of, let's say y equals x squared plus 1 to power 10. So of course, if you want to expand, one way to calculate the derivative of this function is to expand it, because we have an identity for a plus b to power 10 or a plus b to power m. But that's going to be very long, right? Because you have to expand it and include all the terms. And then, we need the binomial coefficients and everything, right? It's going to be very long. And then you can differentiate term by term. Like I said, it will be very long, especially because the power is 10, which is rather a big number compared to 2 or 3. So we don't want to expand right now. Our preference is to use chain rule. And if I can write it as a composition of two functions, then I can apply chain rule. Chain rule is for the derivative of composition of two functions. So solution, note that we can write y equals, let's say, f of g of x, right? With, so what is f of x and what is g of x? So I can set f of x to be x to power 10, and u equals g of x to be x squared plus 1, right? So if I set u equals g of x as x squared plus 1 and f of x as x to power 10, then f of g of x will be x squared plus 1, the whole thing raised to power 10. So now I can apply the chain rule. So thus, note that y equals this with this, then by chain rule, what can we say? We can say that dy to dx, which is like f of u, the whole derivative, is u prime times f prime of u. Now, what is u prime? So here, u prime, u is x squared plus 1. So u prime equals x squared plus 1 derivative, and that's, of course, 2x. And what about f prime of u? To find f prime of u, first I need f prime of x. F prime of x, what is it? F prime of f of x is x to power 10. So f prime of x is x to power 10 derivative, which is 10x to power 9. So then f prime of u will be 10u to power 9, right? It's just a concept from high school that you knew that, if you have a function, let's say, for example, you have a function h of x equals 10x to power 9. And let's say you want to find h of u. What should you do? You just need to replace every x with u. So here f prime of x is a function. The formula is 10x to power 9. I want to find f prime of u. F prime of u, that means I have to replace x with u. So f prime of u will be 10u to power 9, okay? So u prime is 2x, so let's substitute back. U prime is 2x times f prime of u. F prime of x is 10x to power 9, so f prime of u will be 10 u to power 9. So 10 times x squared plus 1 to power 9. So how much is that going to be? So this is going to be 20x times x squared plus 1 to power 9. So this is dy to dx, 20x times x squared plus 1 to power 9. Right, so without expanding our expression, x squared plus 1 to power 10, we could calculate the derivative just using chain rule, 20x times x squared plus 1 to power 9. So similarly, we can generalize this concept, right, to, let's say, any function u to any power m. Okay, so but before that, I can also write the solution. If you want to write the solution in the Leibniz notation, let me also tell you how you can do it. So writing the solution in Leibniz notation. So see y is equal to, what is y here? Y is equal to u to power 10. And u is x squared plus 1. So if you want dy to dx, in Leibniz notation, we said dy to dx is dy to du times du to dx. Right? So dy to du, y is u to power 10. So that means derivative of u to power 10 respect to u. What is that going to be? 10 times u to power 9. See, y is u to power 10. So this is a little bit tricky. So it's sometimes confusing for some students. So y is u to power 10. But what do I want to find? The question asks me to find dy to dx, which means derivative respect to x. So some students here get confused. They say, okay, y is a function of u here. How come we want to differentiate y respect to x? Well, yes, y is a function of u, but u itself is a function of x, right? So ultimately, y will be a function of x. So I can have two perspectives, two approaches. I can look at y as a function of u and differentiate respect to u, but u itself is a function of x, so I can also differentiate y respect to x, or look at y as a function of x. So here we want to find our ultimate goal is to find the derivative of y respect to x, but Leibniz notation, or chain rule in Leibniz notation tells us that to do that, I can first differentiate y respect to u. Derivative of y respect to u, because y is u to power 10, is simply 10 times u to power 9. I should also find derivative of u respect to x. Derivative of u respect to x will be 2x. So that's it. And then 10 times u to power 9 times 2x, if you want your final answer in terms of x, because you want to find derivative of y respect to x. And so we want to look at y as a function of x, right? So it makes sense that we want our final answer to be also in terms of x. So I can replace u with x squared plus 1, then to power 9 times 2x. And then the answer will be 20x times x squared plus 1 to power 9. Which is same as the previous answer. So now if you want to generalize this concept, this example, generalization, let's say derivative of a function of the form, let's say u to power n, where u equals g of x is a function of x. So let's say y equals u to power n, then what will be dy to dx? So again, we can use the same idea. So previously we had u to power 10. We saw how to find the derivative. Now we can use the same idea to calculate the derivative of a function of the form u to power n. So dy to dx, the dy to dx, we know that by chain rule, dy to du times du to dx. Dy to du, y is u to power n, so derivative respect to u is simply n u to power n minus 1. So this is by power rule. And then derivative of u respect to x means u prime. So the answer will be n u prime u to power n minus 1. So what can we say? So we can say that u to power n derivative is n u prime u to power n minus 1. U to power n derivative is n u prime u to power n minus 1. So for example, let's say 1 over, so find d to dx of, let's say 1 over x squared plus 1. D to dx of 1 over x squared plus 1. So what is u here and what is n? If you want to apply this rule here, what is u and what is n? Okay, so first let's write the given expression in the following form. We have, note, we have 1 over x squared plus 1. So I can write it as x squared plus 1 to power minus 1, right? So here I can say that, so we can say that u is equal to x squared plus 1 and n is equal to minus 1. U is x squared plus 1, n is minus 1. So what will be the derivative? So thus we can say that 1 over x squared plus 1 derivative will be, remember the formula, u to power n, derivative is n u prime u to power n minus 1. So here I can say that the derivative is minus 1, u prime is 2x, and x squared plus 1 to power u to power n minus 1. N is minus 1 itself. So minus 1 minus 1. And then this is minus 2x times x squared plus 1 to power minus 2. I can write this one as minus 2x over x squared plus 1 to power 2. Because we know a number or expression to power minus 2 means 1 over that expression to power 2. So minus 2x over x squared plus 1 to power 2 is the derivative of this function, which we solved it using chain rule, like u to power n derivative. Of course, you could solve this one with quotient rule as well. Solution 2, using the quotient rule. So 1 over x squared plus 1 to power, 1 over x squared plus 1, derivative is equal to 1 u prime v. Remember the formula for u over v derivative? U over v derivative is equal to u prime v minus uv prime divided by v squared. So 1 derivative times x squared plus 1 minus x squared plus 1 derivative times 1 divided by x squared plus 1 to power 2. Now, one derivative, a constant derivative of a constant function is 0. So first term vanishes, and then the second term, minus 2x will survive, divided by x squared plus 1 to power 2, which is the same answer as what we did for solution 1. So same answer as above. Okay, so another example I want to do here. So suppose that the tangent line to the graph of y equals 1 over x squared plus 1 passes through the point 2 and 0. Find the equation of this tangent line. All right, for the solution, we know that to find the equation of the tangent line, we need the slope of tangent line, which can be found using derivative. And of course, we need one point on the line. The point on the line is given. And then we can use the slope and the point to find the equation of the tangent line. So first, let's write down the derivative of this function. So y prime, we saw that y prime is 2x over, so minus 2x over x squared plus 1 squared. So this one we calculated above. Right? And the point here, what is the point? The point is 0 and 0. So if I replace x with 0, then what do we get? We get, so the point is 2 and 0. The point is 2 and 0. So if I replace x with 2, what do we get? We get minus 4 over 5 squared. That's minus 4 over 25, which is my slope, right? The x value is 2. I replace x with 2. I got y prime as minus 4 over 25, which represents my slope. And then the equation of the line will be equation of the line. We know it's y minus y0 equals m times x minus x0. And then x0, y0 is also given y minus 0 equals m, which is minus 4 over 25 times x minus 2. Y minus y0 equals m times x minus 0. We have all the necessary quantities. Seems that the screen is freeze. Let me see. Okay, I can stop. Okay, here. Which means, y equals minus 4 over 25x plus 8 over 25. So do you think this solution is okay or no? We found derivative, which we did in previous example with 2 different methods. And the point was given, we replaced x value. We found the derivative at that point, which is the slope of tangent line. We also had the point, we found the equation. So do you think this solution is okay or there is some mistake? The answer is yes, there is a mistake. This solution is wrong. Why is this solution wrong? So let's look at the steps that we followed. First, we found the derivative. Well, this derivative formula for sure is correct. We verified it with 2 different methods here in the previous example. And then the point 2 and 0 was also given in the question. So there could be no mistake there. And then we replace the value of x with 2 into the formula for derivative to find the slope. This step is wrong. Why? Because yes, for the slope, to find the slope, we have to replace x with the x0 that is given to us, but with the condition that x0 and y0 is a point on the graph. If you have a point x0 and y0 on the graph, and you want to find the slope of tangent line at x0, then you can replace x with x0. But here, the point 2 and 0 is not on the graph. So this is exactly the tricky point of this question. Normally, when we, in the past, when we asked such question, I would have given you a point which is on the graph. Let's sum x0, y0 on the graph. And then to find the slope of tangent line at x0, you just replace x with x0 in the formula for derivative. But this point 2 and 0 is not on the graph. Why? Because if I replace x with 2 in the formula for the function, the y value which I will find will be 1/5, not 0, right? So 2, if the point was 2 and 1/5, then I could use this approach. But because 2 and 1/5 is on the graph, but 2 and 0 is not on the graph. So let me explain here wrong, because the slope of, so let me write it this way. If x0, y0 is a point on the graph of y equals f of x, then the slope of tangent line at x equal x0 is given by m equals f prime of x0. However, in this question, 2 and 0 is not or does not lie on the graph. Does not lie on the graph of y equals 1/x² plus 1, since 0 is not same as f of 2, which is 1/5. So the approach above is wrong. So this is the reason for this solution that is wrong. Now, what is the correct solution? So correct solution the tangent line described above is, of course, is tangent to the graph of y equals f of x equals 1/x² plus 1. So it is, of course, tangent. See, why was this approach wrong? Because to find the slope, we replace x with 2 to find the slope of tangent line. We said this is wrong because it's not tangent at x equals 2. It's not tangent to the graph at x equals 2 because 2 and 0 is not on the graph. But it is tangent at some point. At which point? We don't know. That's not given. It just says that this line that we are trying to find this equation, we just know it's tangent to the graph. Of course, it's tangent graph at some point, but at which one we don't know. That's not given. It says that that tangent line, which is tangent to the graph at some point, it also passes through the point 2 and 0, but it's not tangent at 2 and 0 because 2 and 0 is not on the graph. So it's tangent at which point? At some point. Let's call it x0. Because we don't know, we want to find out at which point. So it's tangent to the graph of this at some point, say x equals x0. our goal is to find this point, is to find x0 using the information given in the question. Let me show you the graph. You can use a graphing calculator to see that the graph of this function looks like this. And this point here is, so see if we imagine some tangent line. Let's say this point here is 2 and 0. See, 2 and 0 is not on the graph, and the graph, the tangent line that passes through 2 and 0 is not tangent to the graph at 2 and 0. It just passes through that point, but it's not tangent at 2 and 0. It's tangent at some other point. I'm calling that other point here. I'm calling the x value of this point x0. And if the x value of this point is x0, the y value will be automatically f of x0. So this tangent line, if I call it L, is tangent to y equals f of x. At which point? At x0, and f of x0, and passes through 2 and 0. So it passes through 2 and 0, but it's tangent at x0 and f of x0. What is x0? We don't know. It's not given in the question. We want to find out. Okay, so let's see whether we can find x0. So what is the equation of L? Equation of L, what is it? Y minus y0 equals m times x minus x0. Now, what is y0? Y0 is f of x0, right? Look at the y value of my point is f of x0. And what is m? M, the slope of this line. Slope of L is m, which is f prime of x0, right? Because the graph is tangent, the line is tangent to the graph at x0, so the slope of tangent line at x0 is f prime of x0. So y minus y0, y minus f of x0 equals f prime of x0 times x minus x0. Now let's replace the values. So y minus 1 over x0 squared plus 1 equals f prime of x. What was f prime of x? Here. F prime of x is this function minus 2x over x squared plus 1 the whole squared. So this is minus 2 x0 over x squared, x0 squared plus 1 the whole squared times x minus x0. Okay, so now this line passes through which point? Passes through the point 2 and 0. So that means if I replace x with 0 and y with 2, then this equation will hold. So I can say that 2 minus 1 over x squared plus 1 is equal to minus 2x0 divided by x0 squared plus, oh sorry, 0 minus, y value is 0, so 0 minus this one squared times 2 minus x0. See, x0 is a constant, right? So for example, let's say y minus 5 equals 6 times x minus 3, for example. How do you check whether this line passes through the point 2 and 0? Yes or no? Well, I have to replace x with 2 and y with 0. If the equality holds, then that means the line passes through 2 and 0. If the equality does not hold, that means the line does not pass through the point 2 and 0, right? So this is the way that I can check whether a line passes through a particular point or not. Now I want this line to pass through 2 and 0. So that means I have to replace y with 0, x with 2, and then check whether the equality holds or no. So then what do we get? Then we get minus 1 over x squared, x0 squared plus 1 equals minus 2x0 times 2 minus x0 divided by x0 squared plus 1 the whole square. Now this cancels with the power. Then I'll get minus 1 equals so if I simplify this, 2x0 times x0 minus 2 divided by x0 squared plus 1. Then I can multiply both sides with minus 1 again. And then I'll get 1 equals minus 2x0 times x0 minus 2 then divided by x0 squared plus 1. So if I cross multiply, x0 squared plus 1 equals minus 2x0 squared plus 4x0. So take everything to one side. And then I'll get 3x0 squared, right? Minus 4x0 plus 1 equals 0. And then I can write this one 3x0, here x0. Here I can say minus 1 and also minus 1 here equals 0. Yeah, and then that gives 3x0 minus 1 equals 0, or x0 minus 1 equals 0. That gives me x0 equals 1 over 3, or x0 equals 1. So I found that there are two choices for x0. x0 equals 1 over 3, or x0 equals 1. Okay, now each of these x0 values will lead to one tangent line. So in other words, there are two tangent lines with the given property. There are two tangent lines at this graph which pass through the point 2 and 0. So the tangent line to the graph at the point x0 equals 1 over 3 will pass through that point 2 and 0. And also the tangent line to the graph at x0 equals 1 will also pass through the point 2 and 0. So let's find the equation of these lines. So equation of tangent lines that pass through the point 2 and 0. So what do we need? Y minus f of x0 equals f prime of x0 times x minus x0. Y minus f of x0. The equation of the line is y minus y0 equals m times x minus x0. But y0 can be replaced by f of x0, right? Y0, you can also see in the graph. Y0 of the point is f of x0, and the slope is f prime of x0. So that's what I did here. So if x0 equals 1 over 3, f of x we know is 1 over x squared plus 1. F prime of x, we know it's minus 2x over x squared plus 1 the whole squared. So then I will have y minus 1 over f of x0, replace x with 1 over 3. What do we get? 1 over 9 plus 1, 10 over 9. equals f prime of x0, replace x with 1/3. So then you get minus 2 times 1/3 divided by 1/9 plus 1, which is 10/9 to power 2 times x minus 1/3. X minus x0. So that means y minus 9/10 equals minus 2/3 times 81/100 times x minus 1/3. So this is the one tangent line. You can, of course, verify that. If you want to check your answer, you can verify whether this tangent line, which is tangent to the graph at x0 equals 1/3, does it pass through the point 2 and 0? Because remember, we were looking for tangent lines that pass through the point 2 and 0. Does this pass through the point 2 and 0? You can check. Verify that we can. We don't have to, unless if the question does not ask us to verify, we don't have to verify. But just for peace of mind, if you have extra time in the exam, you can verify if you like. So we can verify that this line passes through 2 and 0. Why? Because 0 minus 9/10. What is it? Is it equal to minus 2/3 times 81/100 times 2 minus 1/3? See, how can I check whether the line passes through the point 2 and 0? If I replace x with 2, this x with 2, and this y with 0, and if this equality holds, meaning that the left-hand side becomes equal to right-hand side, then I can say that the line passes through the point 2 and 0. If this does not become equal to this, then it won't pass through that point. So let's see whether these are equal. So left-hand side is, of course, minus 9/10. Right-hand side, I can simplify it as minus 2/3. 81/100, and 2 minus 1/3 is 5/3. So 2 times 5. So this one, we can say it as minus 10/9 times 81/100, right? Because 2 times 5 is 10, 3 times 3 is 9. And this means minus 10/9 times 81/100 means minus 9/10. So the line passes through the point 2 and 0. So for the other line, if x0 equals 1, so one point of tangency was 1/3, the other one was 1. So again, we can find the equation of the line. So y minus f of x0 equals f prime of x0 times x minus x0. So then we get 1 y minus 1/, remember f of x, I wrote for you here. F of x is 1/x squared plus 1. F prime of x is minus 2x over x squared plus 1 the whole squared. So if x0 is 1, f of x0 will be 1/5. And f prime of x0 will be minus 2 over x0 squared plus 1 the whole squared. So 5 squared times x minus 1. So y minus 1/5 equals minus 2/25 times x minus 1. Oh, sorry, x0 is 1. So f of x, let me write again here, f of x is 1/x squared plus 1. F prime of x is minus 2x over x squared plus 1 the whole squared. So if I replace x with 1 in the formula here, if I replace x with 1 over 1 squared plus 1, that's going to be 1 over 2, not 1 over 5. So this has to be 1 over 2. And then replace x with 1 here, minus 2 over 2 squared, not 5 squared, 2 squared. 2 squared. So 2 over 2 squared means 2 over 4, which is 1/2. So y minus 1/2 equals minus 1/2 times x minus 1. And again, we can verify that this line passes through the point 2 and 0. Why? Because, again, if I replace y with 0, 0 minus 1/2 equals minus 1/2 times 2 minus 1. If I replace y with 0 and x with 2, I'll get this, and minus 1/2 is equal to minus 1/2. So this line passes through the point 2 and 0. So I have two solutions. So one line is this and the other line is this. Both these lines pass through the point 2 and 0. They are both tangent to the graph that is given to us, but not at x equals 2, at some other x0 values. One of them at x0 equals 1 over 3, one of them at x0 equals 1, but both of them will pass through the point 2 and 0. All right, so let's look at some more applications of chain rule. Applications of chain rule. So we already calculated derivative of a function of the form u to power n. What about, let's say, derivative of a function of the form lnu, let's say. So let's say let y equals lnu. Find dy to dx. So again, just use the chain rule. What does chain rule tell us? It says that dy to dx is equal to dy to du times du to dx. Now dy to du, lnu, derivative of lnu is 1 over u, derivative of lnu respect to u, right? If u is your variable, then derivative of lnu, of course, will be 1 over u times du to dx. Du to dx means u prime. So this is u prime over u. So we can say that lnu derivative is equal to u prime over u. lnu derivative is equal to u prime over u. So for example, let's say ln x squared derivative. My u here is x squared, so I can say that it's x squared derivative over x squared, and that's 2x over x squared, which is 2 over x. And ln 2x derivative, if my u is 2x, then derivative will be 2x derivative divided by 2x. That is 2 over 2x, which is 1 over x. So these are consistent with the calculations we have done before for finding derivative of ln x squared and ln 2x. If you remember, we already did these calculations. Here I can show you ln. Here, ln x squared f of x equals ln x squared. But in the previous this example we did in another way, but our answer is the same. See, ln x squared derivative is 2 over x, ln 2x derivative is 1 over x. which is exactly the answer we got here. Okay, and then let's look at another example. Let's say y equals ln 3x cubed minus x squared. Let's say x times this, x times ln x cubed minus 2x squared, let's say. Find dy to dx. So dy to dx, we need to use the product rule first, because see, I have product of two functions, x times ln of some function, right? So use the product rule. Then what do we get? We get dy to dx equals, so derivative of x, right? Product rule says derivative of x times ln x cubed minus 2x squared plus x times derivative of ln x cubed minus 2x squared. Now, derivative of x, of course, is 1. So 1 times ln x cubed minus 2x squared plus x times, now for the second term, I need the derivative of ln x cubed minus 2x squared. So this is a function of the form ln u. If I need derivative of a function of the form ln u, what will be the answer? The answer will be u prime over u. We just said it, right? ln u, derivative is u prime over u. So the derivative of this function will be x cubed minus 2x squared divided by x cubed minus 2x squared derivative. And then this is going to be ln x cubed minus 2x squared plus x times, so x times that fraction, if I multiply with top, it will be x to the power 4 minus 2x cubed divided by derivative of denominator. So it's going to be 3x squared minus 4x. So this is dy to dx. Another example, let's say y equals ln absolute value x. Find dy to dx. So ln absolute value x, first of all, we have to note that the domain of this function is what is the domain of ln absolute value x? Well, if you have a logarithmic function, the expression inside logarithm has to be positive. So note the domain of y equals ln absolute value x can be found as follows. So we need to require that absolute value x, which is expression inside logarithm, has to be positive. Well, absolute value x is always non-negative automatically. If you want it to be positive, that means you just need to require x to be non-zero. So this happens if and only if x is not equal to 0, which means that x belongs to r minus 0. So domain is r minus 0. Okay, so we'll find dy to dx on r minus 0, which is the domain of the function. Of course, we cannot find derivative outside of the domain. So in the best case scenario, a function could be differentiable on all the domain, but of course not on a set bigger than the domain. So what is dy to dx now? So we want to find it on the set r minus 0. So now dy to dx, That means d to dx of ln absolute value x. Now, if I want to get rid of absolute value x, I know that x is in r minus 0, which means x is not equal to 0. So it's either positive or negative, right? So if it's positive, what will be output of absolute value x? If x is positive, then absolute value x will be x itself, right? According to a definition of absolute value x, absolute value x equals x itself if x is positive. So then this is d to dx of ln x, which is 1 over x if x is positive, and d to dx of ln minus x, right? If x is negative, absolute value x by definition is minus x. So then I'll have d to dx of ln minus x, which is going to be by chain rule, because we know that ln u derivative is u prime over u, right? See, that's what we said about, let me show you one more time. Ln u derivative is u prime over u. So ln minus x derivative will be, so let me write down the chain rule, ln u derivative is u prime over u. So ln minus x derivative will be minus x derivative divided by minus x. So that's minus 1 over minus x, which is 1 over x, if x less than 0. Well, that's very interesting. The output is 1 over x in both cases, whether x is positive or x negative. In any case, the output is 1 over x. So what can I conclude? I can conclude that d to dx of ln absolute value x is equal to 1 over x for x inside r minus 0. This is a very important result. In Math 114, when you learn about antiderivatives, you will see that the antiderivative of 1 over x is ln absolute value x. Many students get confused in that point, that they say, why absolute value x? So the reason comes from here, because derivative of, well, of course, derivative of ln x is 1 over x. Derivative of ln absolute value x is also 1 over x. So then some people say, okay, antiderivative means, derivative of which function is 1 over x. When we say antiderivative of 1 over x, means we are looking for a function whose derivative is 1 over x. Where this you will learn in Math 114, but I just want to tell you the idea here because we mentioned this result. So some people say, okay, derivative of ln x is 1 over x, derivative of ln absolute value x is also 1 over x. So why do we say antiderivative of 1 over x is ln absolute value x? Well, the reason is ln absolute value x has a bigger domain, right? So of course, our preference is to write a function which has the domain as big as possible. Okay, so, but don't worry about this. You will learn this in Math 114. I just want to mention this quickly. But for now, you just need to learn that derivative of ln absolute value x is 1 over x, which is same as derivative of ln x itself. So it's a little bit surprising in the beginning because ln absolute value x, if x is negative, becomes ln minus x. But when you differentiate, according to the chain rule, you will have minus x derivative divided by minus x, and these minus cancel out. And again, you will get 1 over x. So the beginning is a little bit surprising, but once you think about it in the context of chain rule, you'll see that why the answer is still 1 over x. So next example, let's say y is equal to, let's say, y equals x to power r. R here is a real number, and you want to find a dy to dx. Note we previously have found the derivative of x to power m, where m was an integer. For the case where m was an integer, we showed that derivative of x to power m is mx to power m minus 1. But then I promised you that I'm going to prove that this rule holds even if m is not integer. So here r is just a real number and doesn't have to be an integer. Still, we will show that the same rule holds. How can we show this? So see, y is equal to x to power r. I want to take ln from both sides. But because x to power r, depending on x and depending on r, could be negative, right? For example, minus 2 to power 3 is negative, right? So, and ln is defined only for positive numbers. So first, let me take absolute value. Absolute value y is equal to absolute value x to power r, which can be written as absolute value x to power r. And now if I take ln from both sides, ln absolute value y will be equal to ln absolute value x to power r. And that's according to the log properties. Log properties, I can write this one as r times ln absolute value x, right? And then if I apply the chain rule, if I differentiate both sides, now differentiate both sides. So what do we get? We get ln absolute value y derivative is equal to r times ln absolute value x derivative. Now ln absolute value y, what is that gonna be? Well, we know that ln absolute value x derivative is 1 over x. So to find ln absolute value y derivative, so note ln absolute value x derivative is 1 over x, right? So ln absolute value y derivative, so by chain rule, ln absolute value y, or u, let me say, derivative will be 1 over u times u prime, right? Because chain rule says that if you have a function, let's say f of x, it has the derivative f prime of x. Now, if instead of f of x, if you look at f of u, what will be the difference? The derivative still will be f prime of u, but then times u prime. So that's the only tricky point in chain rule, that is the normal derivative that you would have if instead of u, you had x, but the only difference is that you have to multiply it with u prime. So when I have x, ln absolute value x derivative is 1 over x. So ln u derivative is 1 over u, but I have to multiply it with u prime. So 1 over u times u prime, where u is a function of x. Here, y is equal to u, a function of x, or u is equal to y. I think here our u is y, which is a function of x. So what can I conclude? So we can say that ln absolute value y derivative is equal to y prime over y. So this is the left-hand side. What about the right-hand side? So left-hand side is equal to y prime over y. Right-hand side, what will be the right-hand side? R times ln absolute value x derivative. So this is going to be r times, r is a constant, right? So derivative of a constant times function is just that same constant times derivative of the function. So r times ln absolute value x derivative. So this is r times 1 over x, which is r over x. So what can we conclude? We can say that y prime over y is equal to r over x. And we wanted to find y prime. Y prime equals dy over dx equals r over x times y. And what was y? Y was x to power r. So r over x times x to power r. And what is that? This is r times x to power r minus 1, right? X to power r, here x to power r divided by x is of course x to power r minus 1. So y prime is r times x to power r minus 1. So we show that x to power r derivative is equal to r times x to power r minus 1. So this is product rule. And valid for, we showed that this is valid for every real number r. Previously, we showed that this product rule is valid for every integer. And now we showed that it's valid for every real number r. So for example, let's say if you want to calculate, let's say, derivative of root x. So y is equal to root x, which can be written as x to power 1/2. So by product rule, we can say that y prime is equal to, what is it? R times x to power r minus 1. So 1/2 times x to power 1/2 minus 1, which is 1/2 x to power minus 1/2. And this is 1/2 x to power minus 1/2 means 1 over x to power 1/2, which means 1 over root x. Right? Negative power means what? X to power minus 1/2. If you have a negative power, it means 1 over the same expression, what with the positive power. So 1 over x to power 1/2, and 1 over x to power 1/2 means 1 over root x. So we show that root x derivative is equal to 1 over 2 root x. Or let's say another example, let's say if you want cube root x squared derivative. So cube root x squared, again, if you write it as a power, what power r should I use? Cube root x squared means x to power 2/3. So by product rule, we can say that cube root x squared derivative is equal to r x to power r minus 1, r x to power r minus 1. So then that's going to be 2/3 x to power 2/3 minus 1. So that is 2/3 times x to power minus 1/3, which is 2/3, 1 over, again, negative power, so 1 over cube root x. So we show that cube root x squared is equal to 2 over 3 times cube root x. And another example, let's say let y equals, let's say root x divided by ln x cubed plus 1. Find dy to dx. So here y is of the form of a fraction. So whenever we have a fraction, we have to use the quotient rule. So use the quotient rule. And what do we get then? So then we get dy to dx is equal to root x derivative times ln x cubed plus 1 minus ln x cubed plus 1 derivative times root x divided by ln x cubed plus 1 the whole to power 2. And then, so this one root x, we just calculated derivative of root x was 1/2 root x. Do you remember? Derivative of root x was 1/2 root x. So 1/2 root x times ln x cubed plus 1 minus, now derivative of ln x cubed plus 1 is, so it's a function of the form ln u. What is derivative of ln u? Derivative of ln u is u prime over u. So then it's going to be x cubed plus 1 derivative divided by x cubed plus 1 times root x. And then ln x cubed plus 1, the whole to power 2. And then this one, I can write it as 1/2 root x times this. So it's going to be ln x cubed plus 1, ln x cubed plus 1 over 2 root x minus derivative of x cubed plus 1 is 3x squared. So minus 3x squared divided by x cubed plus 1 times root x. And then the whole thing divided by ln x cubed plus 1, the whole to power, and the whole thing to power 2. So that's the final answer. You can leave it like this. So please note that some people think that they can move this power to the front. That's not true, because see, we are raising the whole, this whole expression to power 2. Yes, if this power 2 was inside, if you had an expression, of the form, let's say ln x cubed plus 1 to power 2, right? If you had this expression, because ln like t to power 2 is 2 times ln t, right? So then yes, you could write it as 2 times ln x cubed plus 1, right? So this one, you have ln of some expression, in the expression inside has a power, then yes, you can move the power. But here that's not the case. You have ln of some expression, you calculate the result, ln of the expression, you calculate the result, then the whole result will be raised to power 2, right? So this power 2 is not for the expression inside log, therefore we cannot move it in front, okay? So please be careful about this. Sometimes a common mistake in the exams. So that's it. So we did this application of chain rule for logarithmic differentiation and derivative of a function of the form ln u. We saw how we can find the derivatives, and we did some corollary of that. For example, derivative of x to power r, or power rule. Power rule where r is a real number. We calculated the derivative. So x to power r derivative is r x to power r minus 1 for any real number r. So we still need to do more applications of chain rule. So we will do next time, we'll do for exponential functions, trigonometric functions. So if you have, for example, e to power u. So far we know how to calculate derivative of e to power x, but what about e to power u? Or let's say sine u. We know the derivative of sine x, but what about sine u, right? So these things we also will do next time, which is similar to what we did for ln, like the way we calculated derivative of ln u using derivative of ln x. So we'll do a similar procedure for exponential and trigonometric functions. But because it's very important, I want to write it down separately and emphasize on it, okay? Yeah, so that's all, and see you guys next time.